All right, hello everyone. Welcome back. Today I am diving into chapter 4 of Richard Hammock's Book of Proof. I'm skipping chapter 3. I looked over it, and there's a lot of good stuff in there, but it's mostly combinatorial stuff, and I really just wanted to dive into the proofs. So I am going straight into chapter 4, and moving on from there. But I do recommend, if you're interested, going back to chapter 3 because there is some good stuff in there. And I might have to go back for certain things in the future, but we'll just take that risk. Okay, direct proof. It is time to prove some theorems. There are various strategies for doing this. We now examine the most straightforward approach, a technique called direct proof. A theorem is a mathematical statement that is true and can be and has been verified as true. A proof of a theorem is a written verification that shows that the theorem is definitely and unequivocally true. A proof should be understandable and convincing to anyone who has the requisite background and knowledge. This knowledge includes an understanding of the meanings of the mathematical words, phrases, and symbols that occur in the theorem and its proof. It is crucial that both the writer of the proof and the readers of the proof agree on the exact meanings of all the words, for otherwise there is an intolerable level of ambiguity. A definition is an exact, unambiguous explanation of the meaning of a mathematical word or phrase. We will elaborate on the terms theorem and definition in the next two sections, and then finally we will be ready to begin writing proofs. 4.1 Theorems. A theorem is a statement that is true and has been proved to be true. We already saw that. You've encountered many theorems in your mathematical education. Yes, yes, yes. Let's see a couple theorems. Let f be differentiable on an open interval I, and let c be in I. If f of c is the maximum or minimum value of f on I, then f prime of c is equal to 0. Suppose f is continuous on the interval ab, then f is integrable on ab. Okay, yeah. Every absolutely convergent series converges. Very cool. Each of these theorems has the conditional form, if p then q, or can be put into that form. Not every theorem is a conditional statement. Some have the form of the biconditional, p if and only if q. But as we know, that can be expressed as two conditional statements. Other theorems simply state facts about specific things. For example, here's another theorem from your study of calculus. The harmonic series 1 plus 1/2 plus 1/3, etc. diverges. It would be difficult, or at least awkward, to restate this as a conditional statement. Still, it is true that most theorems are conditional statements. Yeah, even this, you could write it as a really awkward conditional statement, but you really shouldn't. It is important to be aware that there are a number of words that mean essentially the same thing as the word theorem, but are used in slightly different ways, right? Corollary, lemma. Oh, there we go, proposition. A statement that is true but not as significant. Proposition, a lemma, whose main purpose is to prove another theorem. A corollary, an immediate result of it, a theorem. Yeah, you'll see them and get used to them. All right, nothing to write down there. This is probably going to be a pretty quick chapter, which is great. It's a great way to get back in. It's been a long time since I've been doing this. Happy to get back into it with something easy as easy as direct proofs. Number 4.2, definitions. A proof of a theorem should be absolutely convincing. Ambiguity must be avoided. Everyone must agree on the exact meaning of each mathematical term. See some definitions. An integer n is even if n equals 2a for some integer a and z. Yep. Two integers have the same parity if they are both even or they are both odd. Other ways they have opposite parity. Pretty cool. Suppose a and b are integers. We say that a divides b, written a divides b if b equals ac for some c in z. In this case, we also say that a is a divisor of b and that b is a multiple of a. A number n in the natural numbers is prime if it has exactly two positive divisors, 1 and n. If n has more than two positive divisors, it is called composite. The greatest common divisor of integers a and b, denoted GCDAB, is the largest integer that divides both a and b. The least common multiple of non-zero integers a and b, denoted LCM-AB, is the smallest integer in n that is a multiple of both a and b. Probably a good one to write down. Okay. So, GCD 18, 24 is equal to 6, because 6 divides both 18 and 24, and nothing bigger does. GCD of 5 and 5 is 5. GCD of 32 and -8 is 8. GCD of 50 and 18 is 2. And so on and so on. Of course, if GCD of two numbers is 1, they are considered, what's the term? Something prime. They actually might have it here. No, but that basically means that they have no common divisors other than 1, which is true for all numbers. Fact, not a theorem, but a fact. If a and b are integers, then so are their sum, product, and difference. That is, if a, b, and z, then a plus b is in z, a minus b is in z, and a times b is in z. Awesome. The division algorithm. Given integers a and b with b greater than 0, there exists unique integers q and r for which a equals qb plus r and 0 less than or equal to r, which is less than b. That's like the remainder. The division algorithm, yeah. You can put any integer into the form any two integers into the, well, let's see. Yeah, I guess even if b is larger than a, you can just make q 0 and r equal to a. So, yeah, I see. Okay. Another fact that we will accept without proof, at least for now. That's funny. This is you'd think we'd see some proof. Well, I guess this is still in the definition section, so. Oh, this is also a different fact. Another fact that we will accept without proof, at least for now, is that every natural number greater than 1 has a unique factorization into primes. Yes, yes, yes. I'm sure we will prove that. We must. By unique, we mean that any factorization of 1176 into primes will have exactly the same factors. Oh, right. It has one and only factorization. Okay, cool. On to direct proof. We're almost done with this chapter. It'll be real quick, and then we get to dive into contrapositive proofs. That's fun. All right, direct proof. This section explains a simple way to prove theorems or propositions that have the form of conditional statements. The technique is called direct proof. To simplify the discussion, our first examples will involve proving statements that are almost obviously true. Thus, we will call the statements propositions rather than theorems. Okay. Sure. Proposition, if P then Q. Oh, okay, yeah. Outline for direct proof. Look at that. Proposition. Suppose P, and then at the end you are concluding Q. Easy as that. Let's see an example. If x is odd, then x squared is odd. Nice. All right, so we're starting with assuming that x is odd. So the first thing you do is just, what's the definition of odd? Go look that up, write that down for x, and then square it. And I'm sure we will just see x squared. Oh, they're kind of working backwards. Hold on. Now jump down to the last line, which says that that's not what I would do, but okay, you can do this. You don't have to do that, though. Think about what the line immediately above it would have to be in order for us to conclude that x squared is odd. By the definition of an odd number, we would have to have x squared equaling 2a plus 1. I see why they're saying this. You should think about where you're trying to go with the proof, so that makes sense. However, the symbol a now appears earlier in the proof, so we should use a different symbol, say b. Bridge the gap. Yeah, see, you just expand this part out. 2 times some integer. You know this is an integer from whatever above that said multiplying and that adding is an integer. And then this is a good last step. I'm glad they include this. Once you've written out all your steps, you go back and rewrite it as a real paragraph. Very nice. Very nice. At least initially, it's generally a good idea to write the first and last line of your proof first, and then fill in the gap. Sometimes jumping alternately between top and bottom until you meet in the middle, as we did above. This way, you are constantly reminded that you're aiming for the statement at the bottom. Sometimes you will leave too much space, sometimes not enough. Sometimes you'll get stuck before figuring out what to do. This is normal. Mathematicians do scratch work just as artists do sketches for their paintings. That's funny. Okay, let a, b, and c be integers. If a divides b and b divides c, then a divides c. That's a good one. That's a good one. Let's see how they do it. So you start with a dividing b and b dividing c, and at the end, you have to conclude a divides c. All right, let's implement what divides means. Yep, yep. Okay, and we need at the end, they kind of skipped ahead. Well, not really skipped ahead, but you can implement this as well. You need something of the form c equals a times an integer, right? But you can plug in ad here for b, and you are going to get c equaling a times some integer, which is what we need. 4.4 Using cases. In proving a statement is true, we sometimes have to examine multiple cases before showing the statement is true in all possible scenarios. This section illustrates a few examples. Our examples will concern the expression 1 plus negative 1 to the n times 2 to the minus n. Here's a table showing its value for various integers for n. Notice that 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4 in every line. Okay, okay. Is this always a multiple of 4? We prove the answer is yes in our next example. Okay. I see what they're talking about. Using yeah, just splitting your proof into multiple smaller proofs. That's what we're doing here. So we got something in here. If n is in the natural numbers, then 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4. Suppose n is in the natural numbers. N is either even or odd. We're going to consider both cases. N is even, then n is equal to k for some k, and negative 1 to the n is equal to 1. Okay, plugging in 2k. So you're getting 1 plus 4k minus 1. Those are canceling. Of course, 4k is a multiple of 4. Then odd. You're getting -1 now. You are getting some extra 1, but you also have a negative out front. These two are canceling. No, excuse me. You're getting 2k plus 2, and then minus 1 means you're going to get a plus 1. Yeah, 4k plus 1 becomes negative 4k minus 1, which cancels with that. Also a multiple of 4. Very cool. Every multiple of 4 equals this equation for some n in the natural numbers. Fine, let's go through it. It's not like we have much more to do. In conditional form, the proposition is as follows. If k is a multiple of 4, then there is an n in the natural numbers for which 1 plus -1 to the n times 2n minus 1 is equal to k. What follows is a proof of this conditional statement. Suppose k is a multiple of 4. Right? This means k equals 4a for some integer a. We must produce an n in the natural numbers that gives us back k when we plug n into that equation. This is done by cases, depending on whether a is 0, positive, or negative. Right. Okay, that makes sense. Suppose a is 0. Then you just put 1 in there to get 0 out. And then a positive a. And this is usually the point where you're going to have to solve. Let's see. This is definitely a case where the solving of the proof is in the opposite order of doing the proof. So like you can see that this seems kind of like the author pulled this out of their ass. That's because they solved for n here. They definitely started with this thing equaling how do they do that? Yeah, equaling 4a. That's right. They had this equal to 4a, and they got rid of this because well, whatever. N is going to have to be that is going to have to be positive if you're ever going to pull it out. And they solved for n, and that's how they got the 2a. So that when they come back through and are writing the proof, you plug this in and it all comes out nicely. Whatever. I realized halfway through, I was like, I'm not interested in explaining that, but I did. See, this one's a little more complicated because you need 1 minus 2a to get it to pop out nicely and give you the 4a that you're looking for. So the above cases show that no matter whether a multiple k equal 4a of 4 is 0, positive, or negative, k equals 1 plus -1 to the n times 2n minus 1 for some n in the natural numbers. Very nice. Okay. Treating similar cases. Occasionally, 2 or more cases in a proof will be so similar that writing them separately seems tedious or unnecessary. Here's an example. If 2 integers have opposite parity, then their sum is odd. Suppose m and n are 2 integers with opposite parity. We need to show that m plus n is odd. This is done in 2 cases as follows. Suppose m is even and n is odd. You're plugging them in, you're getting an odd number out, and then you're doing the opposite. Yeah, in either case, m plus n is odd. They really are the same case, but you're just really covering all your bases. The two cases in this proof are entirely alike, except for the order in which the even and odd terms occur. It is entirely appropriate to do just one case. I mean, it really is just one case, though. To be honest, it is just one case. But I guess that's just semantics. All right. In a similar spirit, it is advisable, at least until you become more experienced in proof writing, you write out all cases, no matter how similar they appear to be. Please check your understanding by doing the following exercises. The odd-numbered problems have complete proofs in the solution section in the back of the text. Okay, let's do a few exercises. Might as well. If x is an even integer, then x squared is even. Okay. Okay, how are we going to start this one? Assume x is even. Even. Therefore, there exists an a in math BBN such that x equals to a. Therefore, x squared equals to a squared, which is equal to 4a times a. Oh no, sorry. 2. 2 is the thing we need to be pulling out, not an a. Squared, which means x squared is even. Boom. All right, let's do 4 next. Proof. Let x and y be odd. So x equals to a plus 1 and y equals to b plus 1, where a, b are in the integers. And what are we trying to do again? Okay, xy is odd. Xy is odd. So let's just multiply them together. I'm sure we will find a way to get an odd number. Therefore, xy is equal to 2a plus 1 times 2b plus 1, which is equal to 4ab plus 2a plus 2b plus 1. Yep, that's right. Which is equal to 2ab, a plus b plus 1, which is of the form of an odd number, which means xy is odd. Go farther down here, maybe do a divides. Yeah, let's do a divides one. Let's do this one. Let's do 11. suppose A, B, C, D are in the integers if A divides B and C divides D, then AC divides BD. Proof of this. We are going to start with just implementing the divides definition. Let A divide B and C divide D, which means that, okay, divides. If A divides B, then B is equal to A times a number, means that B equals X times A, and B equals Y times C for some XY in the integers, right? That's divides. I'm going to double check that to make sure I'm not making an embarrassing mistake. Yeah. Yeah, okay. I'm not making an embarrassing mistake. And we need to get to the point where A times C divides B times D. I think we need to multiply B times D. Thus, B times D is equal to XA times YC, which is equal to XY AC, which means that AC divides BD. Done. Okay, there's a couple of interesting ones here. We should do a choose. Okay, let's do one of these that are like for real numbers, because I feel like that will be kind of fun. What is this one? Suppose x, y is in R. And they have... I think this is a good one. Wow. X equals y or x plus y. Yeah, let's try it. It's kind of interesting. Suppose x, y in the real numbers, if, where are we at, 13, if x squared plus 5y is equal to y squared plus 5x, then x equals y, or x plus y equals 5. Here, I think the main thing is going to be, I think this is just like a, you might be dividing by 0 thing. That's probably why that, I suppose. But let's just make sure that we do it correctly. Like just doing the proof correctly is kind of the main thing here because the or is kind of a weird thing. Um, because it can be, you have two different possibilities. Shoot. Two different conclusions that we can reach. We haven't gotten contradiction yet. I would probably use I might use contradiction or something, but I mean, we know how this is going to start. Let x squared plus 5y equal y squared plus 5x. So I think we would want to assume that x plus y is not equal to 5, and we want to reach x equaling y, or the other way around. Yeah, I think that's what we're going to do. And x not equal to y. And at the end, we are going to conclude this is what we want to get to at the end. Then what are we going to get? We need to get this into the form x plus y. Uh, let's just move everything. If we move everything to the side, I'm just gonna see what this gives me here. Minus y squared minus 5x equals 0. I don't know if this is the avenue to be going down, but let's just see. Ah, okay, we can factor. I think that's actually, we probably don't even need this. I think we factor this into. Hmm. Let me just see what a factored, what this looks like factored. I don't know why I did that. I didn't really want that. X times x minus 5 plus y 5 minus y. No, that's not the right way to factor. That's equal to 0. Can we get a term that is x? Can we get this completely factored? Can we get it of the form x plus y times something? Maybe x minus y. Actually, x minus y seems better to me. Can we get it like this somehow? X minus y times something here equaling 0. That's what I would like. It just doesn't seem like the way to do this problem the more I'm looking at it. This is almost it. X minus y and x plus y. Actually, is this it? Is this actually what it is? I think it needs to be y minus x. No, it's x minus y. Because we need the x squared to be positive. That's right. Yeah, hold on. This is right. Because when you factor this out, you're going to get x squared plus xy minus 5x minus yx, which cancels with the xy, the positive xy, minus y squared. Yeah. Plus 5y. Yep. Okay. Which can be factored into x minus y times x plus y minus 5 equaling 0. Yeah, we don't need this. This. Can I be that? I say this equation is only true if one of those two are true. Yeah, this means, let's just say this. We can conclude that either x minus y equals 0 which means that or x equals y, or x plus y minus 5 equals 0. In other words, either x equals y or seems fine. Seems like a fine way to end it. Maybe it could be worded a little better. But we got there. Which one to do next? Oh, let's try 21. This has primes and it has the binomial factor equation. And then I think we're gonna do 20. We're gonna do 21. We're gonna do 26. And then maybe 27. 21. If P is prime and K is an integer for which 0 is less than K is less than P. Then P divides. Okay, what? How do you do this one again? I think it's this. P choose. Okay. Did that give me what I want? It did. Proving this. Always a solid way to just start with our assumption. Let P be prime and oh, that's not what I wanted. Prime and K in Z such that 0 is less than K. It's less than not capital P. All right, I'm going to do this. We're going to do a little bit of this here because I need to write out what the choose is. I want to see the choose. P choose K. Let's see, fraction. All right, they gave this to us in chapter 3 that I skipped, but I did read some of. But I always forget what the exact equation is. So n choose K. Pretty sure it's n factorial p factorial k factorial times p minus k factorial. And what do I have u capitalized? I am almost positive that is the equation we need. Okay. And we want to conclude that P divides that thing? So we need to conclude this. Need to conclude that this thing is equal to P A integer. Okay. This one might be kind of hard. Okay. I have an idea. We might not need cases, but I'm just thinking we do the case where K is equal to P minus 1. And then the cases where K is less than P minus 1. Because it really seems like you can just pull P out of this, right? Because you can just rewrite this as P minus, oh god damn it. P minus 1 P times that. So we really just have to show that this is an integer. We know that k is less than or equal to p minus 1. We haven't even used the fact that p is prime yet. Like, what does p being prime have to do with this problem? This is really what we need to do. Need to show is an integer. Right, that's what we need to do. We need to show that that's an integer. Get out of here. This is our goal. How can we show that? This is a hard one. I mean, can we say we know that I've never proven it, but I mean it has to be that the binomial factor is always an integer. Did we ever prove that? I'm gonna have to go back and see if we've proved this at some point. I guess we did have to go back to chapter 3 sooner than I thought. I want to just assume that this is an integer always without proving it. I mean, it has to be, right? It has to be. Let's assume. Let's do a little bad student work here. Okay. We're going to be kind of bad students. But we know that this is an integer. If we know that that's an integer, then, and we know that p is an integer, then we know that the other part is an integer, right? No. That's where the primeness of this comes in. That's why it has to be prime. Because let's see, there's like a lemma here that's if we can have a little lemma, if p is prime and p, we didn't this didn't just get proven, did it? Like in the problem right before this? No, but I think we could just prove our little lemma here. If p is prime and p a is an integer, then a is an integer. Almost positive you can prove this. Not true for all numbers because an even number PA uh, greater than 1. Ooh, can't be 1. Can't be 1. Because or else you could have 1 over p. It's not an integer. P is prime, but I feel obligated to prove this because I'm not going to prove the other thing about the binomial coefficient equation. All right. Let P be prime and PA greater than 1. Be an integer. And good enough. Kind of sloppy, but whatever. And I might even just do this. Really doesn't seem like the way to prove this, though. There's probably some way simpler way that I'm just missing. But I see the line. I see this line, and I'm gonna take it, and I'm gonna finish it this way because I'm almost positive that this works. It's just probably I'm overcomplicating it. But hey, we're gonna get a little lemma out of this, which is cool. Um, A is I don't even know if that's gonna be possible. Wait. I thought this was gonna be easier than this. Uh, P is prime, and P times A is an integer. And I want to prove that A must be an integer. This is not. It's blowing my mind. This is not true for all n. I mean, for anything. Like, why does P have to be prime? Why does P have to be prime? Doesn't everything divide the binomial coefficient? Like that setup? Because you just pull out the first part of the factorial on top. But it must be that this other portion is now not always an integer, which is why I was thinking I would need this lemma. Dude, I don't know what to do for this problem. This is crazy. K factorial, P minus K factorial. There must be some way to manipulate this. I just don't know. I don't know how to implement the P being prime. I have to look. I can't do this one. Let's go to the back of the book. We are in section 4.5, number 21. I'm glad this is an odd one. It would have sucked if I couldn't figure it out and I didn't have the solution in the back. From the formula, using the binomial coefficients. Did I at least get that right? I did. Oh. Wait. Now, since the prime number p is a factor, it must also be a factor of this big thing on P choose K times P minus K factorial times K factorial. Okay. P appears in the prime factorization of that. Okay. Don't say similarly the prime factor. Why? Why can you conclude that? Wait. I don't what? Hold on. You can't just say that. How did you get that? Oh, because P minus K is less than P, because K is greater than 0. Yes. Oh, no. No. It's, wait, this is now K is a product of numbers smaller than P. I see. You're looking at the prime factorization. All of its primes in the prime factorization have to be less than P. I guess that makes sense, but I never. Okay. If you can write out a composite number as a set, as a product of a bunch of numbers that are all smaller than a prime P, then P can't be in the prime factorization of that number. That's an interesting lemma. I guess I'd never thought about it. I've also never proven it. If, but this is kind of the point that he's using. Well, let's read the. You noted that the prime factorization must contain a p, so the prime factorization of p choose k contains a p. Okay, let's do if p is prime number and c is a number that can be expressed as a product in the form c equals c1 times c no, times c2 times c3 no, times dot 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 times c sub n such that c sub I is less than p for all I less than or equal to n, then he is not in the prime factorization of C. That's basically what he's using here. Which intuitively makes sense. Should we prove that? I'm going to do this later. I don't want to do it right now. But it seems important, and I'm pretty sure it comes up later. I'm pretty sure this comes up more often, which is why I'm like highlighting it now. Because I have seen that before. Because I think you use it in like the uh infinitude of primes proof. I'm almost positive it comes up there. Anyways, very good proof. I like that he uses the prime factorization. I'm going to write this out. Since k is less than p, using our lemma below, p is not in the how did he okay. Let's just write it out like that then. Since p actually hold on. And is therefore let's just say then p is in the prime factorization of p factorial, which also means that p is in the prime factorization of that. Okay. He's not. Not in the prime factorization of k factorial. And similarly, since I like writing this out, since p minus k is less than p, then p is not in the prime factorization of p minus k factorial. Therefore, it must be that p is in the prime factorization of p choose k, and so p divides boom, done. Awesome. All right. Man, what a problem. I think I only have time for one more of these, and I think I'm going to do 27 because it looks easy, but I could be eating my words here in a moment. Assume this. Let's just give it. I will probably be using something. Here's one. And so let's just write this out. A equals cx and b equals cy for some xy in the integers, or technically natural numbers. whatever. I guess I'll just stick to the natural numbers. Okay. Um, if B is prime, yeah, we can assume B is prime to start and get that B divides A. And then we can assume that B does not divide A and conclude B is prime to show that it must be one or the other. Seems like a fair way to do this, I think. Okay, first assume B is prime. And so it must be that C is equal to B because the only thing could be C and Y. One of them is 1 and the other is B. And since C cannot be B, it means that and since C and EQ1, it must be that C equals B and Y equals 1. Therefore, A equals B, X, and so B divides A. Okay, we concluded that. Now, assume B does not divide A. And I need to show that B is a composite number. We're assuming B does not divide A. What can we draw from that assumption? There's no integer such that A equals B times that integer. It just doesn't cleanly. If B does not divide A, okay. Okay, this means that we know that C is not equal to C, yeah, is not equal to B, and since C not equal to 1, then B has to be composite since CY is a multiple. It must be that. Yeah, then B is composite since C divides B. Right. There we go. Kind of roundabout. I feel like I could have done that one better, but the or is kind of weird. Like the or makes it I just feel like makes it an awkward proof anytime. Like whenever, because you're actually you're proving two statements. All right, cool. That's that. Next up, chapter 5. I'll see you guys then.